This conference will now be recorded.
Thanks,
All right,
Boppy.
Cliff.
Yeah, thanks, Boppy. So first, let's talk about OCP APAC Tech Day, which is going to be July 4th in Seoul, Korea. The main sponsor working with OCP is Samsung to do this. And it's timely that, Kevin, you're on the call. It turns out that I have been trying to encourage the organizers at Samsung to include a chiplet half-day track or some presentations around chiplets. And I think they haven't, and so they're still looking for someone that might, from APAC, that might be able to step up and help drive the content for that track, as the presentations are typically by invitation only for this event. So Kevin, I wanted, and the rest of the team, rest of the community, I wanted to bring that to your attention in case there's someone that could potentially lead that. I'm happy to present potentially there since I'm going to be attending, but I couldn't lead it. And so I wanted to just put that open to the community. Kevin, you may want to connect with Young Soo on that. If you don't know who that is, I can make an introduction. And then moving on, I would wanted to mention that the call for papers is open for the OCP Global Summit, 17 to 19 in San Jose, October. And Boppy and I would very much like to negotiate a half-day chiplet track at Global Summit. In order to do that, we need the ammunition, which is everyone here who can, please put in a proposal for a presentation. Boppy and I will also be working in the background and reaching out to select folks to encourage you. But while we're here on the call, I just wanted to mention that if you can do it, please put in a call for participation, put in a proposal. The proposal itself is a 1,000-word abstract to get you started. You don't need to have a paper ready to go. Okay, Boppy, I think those are the things I wanted to share with everyone.
Hey, Cliff, can you shoot me an email with that information, and I'll follow up with you on it?
I will.
So yes, everyone, if you could please submit an abstract. We're really interested. We really like platform proposals like this from Suresh from last week and other people around the world. Progress in using CDXML, either in EDA tools, any innovative thoughts you have in chiplets, implementation information for Bow or the link layer, or any reference architecture information you'd like on top, you're thinking of on top of this. So we'd love to hear about any and all of those at the Global Summit. Is that fair enough, Cliff?
Yes, Boppy, and we'll obviously have you doing an update on the open chiplet economy. And I'm hoping that we're going to have a couple of really important announcements that we can do in front of Summit, maybe around the open chiplet marketplace getting started at the OCP marketplace. So stay tuned, it's early days. We're working on it in the background.
Yes, so we'd really like to emphasize the economy part of our progress. So anything you have in that space, we'd love to hear about it. And on that bright note, Samsung, Cadence, and Fraunhofer, we're very happy to have you. Kevin, thank you. It's all yours.
Okay, thanks. Hey, thanks for the opportunity. And in light of what Boppy and Cliff just shared about, I think it aligns very well. We thank you for the opportunity to just share with the group here what's going on. Aligned with what OCP and ODSA is trying to do is really building a chiplet economy, an ecosystem. And what we've done is we put together between Fraunhofer, Cadence, and ourselves, Samsung Foundry, our own kind of platform that we started building. And it's really about collaboration. How do we work together? We know that we all know, and you guys are all familiar, chiplets has been around for a long time, but it's really been vertically integrated within one company where you have control of everything. To build an ecosystem and an economy around it, we need this standardization, and we need collaboration, we need interoperability, and all of these things. And that's what we found is we wanted to start with the three of us, and we started talking about what we need to do. And actually, since we started the project, we've actually had others come into this as part of our ecosystem as well. And we'll share a little bit about that moving forward as well. But the goal is really to innovate, is how do we build this chiplet ecosystem and what needs to be done. And in the process, we've learned quite a bit. To have silicon proven chips, but not just chips, a platform where you can actually build things. And the whole goal is to help customers accelerate their designs, build the products faster, and all the things that I think we've been all kind of promoting out there about lower cost, lower the risk, and just really accelerating this concept of chiplets and what it can do for the semiconductor market. So what we've done is we built this around the BOW die-to-die interface right now. And with that, just a little bit of background is, so we started this with Fraunhofer leading the design area. And Fraunhofer is a research institute that has done a lot of research in a lot of different areas, everything from in packaging and chiplets and antennas. And they're really moving away from just pure research, but into implementation. And so that's what Fraunhofer has done here, is they've taken the lead on a lot of the design portion of this, driving the BOW IP, driving the chiplet design as well. At the same time, what we've done is Cadence has moved away from just being an EDA and IP company and moving into really system design and intelligent design to that point. So chiplets becomes a very important part to them. It's not just about having the EDA flows or the right IPs, but how does this work as a system in terms of today's economy, what needs to be done, what marketplaces it needs to go into, and they've done a lot of that. For Samsung, our role in this has really been manufacturing. You know, I represent the Samsung Foundry portion of it, and it's really about advanced nodes that we're driving right now, which I think is the lead on chiplets. But I think people forget that the whole concept of chiplets and heterogeneous integration is about the N-1, N-2. You don't need to do everything on the most advanced nodes. So we're trying to do that for advanced nodes as well as the more mature nodes to enable chiplets in that area. And I think people in concept understand that, but if you see what's being enabled today, it's primarily only the advanced nodes. And what we're going to do is we're looking at it from a system perspective. But also the role of Samsung is really building this ecosystem. You know, we're kind of agnostic to things. You know, we manufacture chips. So I'm trying to build as many partners and an ecosystem to enable chiplets as much as possible, starting with Cadence and Fraunhofer. But as I mentioned, we've already expanded that to a variety of other partners that have jumped into this. So that's really the goal here, is about having a reference platform and enabling chiplets to be designed. If you see on the top there is Cadence, Samsung, and Fraunhofer, but already we've had Exenergic join our ecosystem, building some SRAM for the design. We are actually talking to companies right now that are building things to add sensors and that are going to be critical to chiplets, and we're seeing that already. So they're going to be building different monitors and sensors that will be integrated into this chip as well. We're talking to other guys who are building chiplets to do interoperability, and I think these are all critical things. So the goal in building this platform is talking about how do you do the chiplet integration? What technologies need to be there? It's not just one IP for the die-to-die, but it's a variety of other things. How do we handle the packaging? How do we do the different process nodes that are there? And that's kind of the goal of what we did for this reference platform, is to really enable this, to gather all that learning about building an actual system, not just building a chip, and understanding where those challenges are and trying to address those challenges before, so we don't have to relearn it over and over again.
Hi, Kevin. This is Ravi from Meta. I have a question.
Yeah.
Hey, I heard you saying SRAM. So is SRAM is a chiplet you are building, or SRAM is like maybe, and how if it's a chiplet, what kind of packaging you're using?
Right now, the SRAM is just for cache and it's not as a chiplet, but we are looking at different packaging options and stacking options, not just for SRAM, but for DRAM and a variety of different things right now. I'm not at liberty to do any specifics, but I believe that that's where the industry is going, and we're working with our memory teams to try to come up with innovative solutions as well.
Thank you.
Okay. So with that, let me give you an idea of what this chiplet's going to look like. Okay. So if you look at a block diagram, we are targeting this for Samsung's 5 nanometer process, which is in full production right now. We've integrated, if you look at the blue blocks in the middle, this is the Cadence Tensilica DSP cores. We've also included their NX and LX for system management. We have a lot of the right IPs that are going to be needed that people want for chiplets, which is PCI 6 and DDR5. And then Xenergic is doing the L2 system memory. So that's what we did. They primarily targeted high performance and low power. And then for this one, we've used the BOW. So the goal of this is a working proof of concept chiplet. We have not, optimized it for the lowest power or the highest performance or anything else, but it's to go through that process of, okay, when you build a chiplet, what are the key blocks there? How do we make sure that everything works together? How do we do the integration and everything else? So the next slide, what I'll show is actually more engineering system architecture. Okay. So what you'll see is we're using an AXI interconnect inside. At the bottom center area, what you'll see is the LX core and X core will handle system management. You see the general GPIOs and bus interfaces at the bottom. At the top, you'll see the die-to-die interface as well as a bridge, because we're going to be talking to some partners that are doing chai, so we want to have a bridge there if it's not native AXI. We have our PCIe there. And then on the right-hand side, you'll see the main core, the DSP cores from Tensilica Cadence, that has a DDR in there as well. And what you'll see is the right and the left-hand side is a duplicate, and that just makes for easier design. As I mentioned, is if I were to build a real chiplet, I may not architect it exactly this way because it's maybe not the most optimized. But for what our goal is as a proof of concept, this gives us the number of lanes for DDR, the PCIe, and kind of the compute power that you want to do.
Kevin, is this a chiplet or this is
This whole thing is one chiplet.
the whole thing is one chiplet? Okay, thank you.
This whole thing is one chiplet.
Oh, okay. So Kevin, the previous page, the diagram that you had, the floor plan, all this is one chiplet?
All of this is one chiplet.
And it's all in the Samsung 5A process?
Correct.
Okay, got it. Thank you.
Okay. And I'll give you an idea of why we did this and what it looks like. Okay. So what we're doing on this design is to bring it up. We want to bring it up as a monolithic SoC first. It just makes it easier to test out and bring up. So in building this chiplet, we're going through the whole RTL design and integration, synthesis, whole thing, packaging, and bring up. Okay, and as a monolithic chip, it can be brought up as an AI or ML core. It could be a vision core. It could be IO hub, whatever. The NX and L cores are used for boot and management, and we have onboard memory. But so this allows us to design it and bring it up very quickly. The goal for after that is having the BOW is to put two of these chips together. One can be configured as one operation, another can be configured as a different operation.
Yeah, Kevin?
Yeah.
The Zeng, you just want to speak your question out? He has a question on chat. Maybe you can just ask it.
Yeah. Hi, Kevin. Just piggybacking the first question that will Samsung provide something like Samsung's HBM PIM chiplets to be a part of a heterogeneous integration platform?
Okay, can you restate the question? It wasn't quite clear to me.
Actually, there is someone. I think there is a team in Samsung's DRAM business doing something called process in memory, that they put some logic circuits in the DRAM chip, in the HBM DRAM chip, so that they claim that they can reduce the data movement in the system. So do you
Right.
think that Samsung will eventually provide such chiplets to be a part of Samsung's heterogeneous integration platform?
Yeah, I can't comment to products that we're doing. Yes, Samsung as a whole is doing a lot of in that area. We are working tightly with memory on a variety of different projects. But speaking for Foundry only, the goal of Foundry is we will not be providing chips. That's not our goal. Our goal is for manufacturing. That's why early on I said this is a proof of concept. We haven't optimized it for anything. It's not like we're going to start building products and saying, oh, come and buy a chiplet from us. That is not our goal. Our goal is on the manufacturing. Now, we are going to work with a variety of partners who are going to be building chiplets on Samsung process. And what you're suggesting could be one of those things. But we're going to be working with a variety of groups internally as well as externally to manufacture to make chiplets available. Does that kind of answer your question?
Uh, yes, and also I wonder whether Samsung's DRAM business will also be open to foundry services, since there are some research groups and some business can ask them to do that so that they can put some processors inside a DRAM chip. I'm wondering whether Samsung will open it to all outside designers.
Yeah, I can't speak for Samsung Memory and what they're going to do, but for Foundry, we're open to working with a variety of customers and partners right now.
Okay, thank you.
Okay.
So Kevin, I do have a question about the application of this chiplet SoC. Is this just a proof of concept? Are you guys doing only proof of concept to flush the flow for potentially tools and packaging? Or this is kind of a real application that you're anticipating?
Both.
What?
And if you hold on to a couple more, I'll show you some slides, and I think that will answer it. Is
Sure,
in the process. In the process, it was a proof of concept to make sure that we flush out having a, working with Cadence. We wanted to make sure that we had a tool flow, a reference flow for chiplets and what to do and all the different tools. We wanted to make sure we had a packaging flow. We wanted to make sure. So a lot of that was to flush out the flow, but at the same time, we wanted to make sure that it was functional. It may not be competitive as a product, but it is functional. And what I'll show is this can work very well as an I/O hub for a chiplet because it has the PCIe in there, it has the DDR, it has the controllers in there to do boot up. So it can easily act as an I/O hub in a real application connected to some kind of accelerator or a compute die. Okay. So kind of to answer your question, the next one is exactly this, is the goal is first to bring it up as monolithic, bring it up, use two of the same dies together to test out the interface, but we're already in discussions to do some kind of custom compute or accelerator on the other side.
Okay, that's what I was hoping.
Yeah.
Sorry, Kevin. That's what I was hoping to see. Thanks.
Yeah. And actually, Andy's going to present on more of the engineering details in a little bit, but as I mentioned, on the left-hand side is the chiplet that we're building right now with the BOW. And actually that BOW was developed by Fraunhofer. On the right-hand side, we're actually in discussions with various partners already that want to test this out. And the BOW that they're using is actually from a different vendor. So what we're talking is about true interoperability. So we're gonna be looking at BOW to make sure, because it's easy if I build both sides and I do everything, I can make sure it works. But our whole goal about this ecosystem is, hey, how do we get interoperability? How do we get different people building different chiplets and being able to talk to each other? We're working out the system stuff too. Is on the compute die, it might be a client die, which means our chip needs to be able to boot it up, understand what it is, configure it, and everything else. So we're going through that whole process right now, working with different partners. So there's a lot of learning that we gained from this, and I've been saying that in building a chiplet, it's not building an SoC. Building a chiplet is building a system. You have to think at it at a system level. And a lot of people that are building chiplets right now are still in the mindset that this is just a different SoC. It's not. it's a subsystem, and you have to understand all of those issues as well. Okay. Any questions? So with that, as a platform, the goal is, hey, we started out with BOW. You can change it to UCIe if you want moving forward. If you go, you can change your PCIe and say, I don't need 6, I'm going to go 5, or I want to go CXL, or I want more lanes or less lanes or whatever. DDR, is changing. Do I want 5600? Do I need 64? Do I want to go to 8400? Do I want to switch that to LPDDR? Do I want to jump to HBM? Depending on your applications, your memory may change. Okay, system memory sizes may change. Your core may change. I might be using an ARM. I might be using a RISC. I might be doing something custom. So those are all the things as a platform allows us to explore and really drive this whole concept of what people are trying to do with chiplets right now. So with that, another key area is packaging. So multi-die packaging, whether it's organic substrate with silicon interposer. This particular one is going to be just an organic substrate to keep it lower cost, easier to move forward. But it's not just about building a chiplet. Andy's going to talk later on about the platform, building a board around it, allowing you to really do testing and stuff. So that's kind of, I'm setting the baseline of what we're trying to do, what our goals were, where we're moving forward to. And Andy's gonna talk a little bit later about, we're gonna build a daughter board for this, but we're planning for a platform to use an ARM-based platforms that are out there in the market already and just plug into it. That way, all of your BSPs, everything, you don't have to develop any of that software to bring it up, and you can focus on the chiplet itself. Okay. So that's kind of the background of this collaboration platform that we've done. I'm going to pass it off to Andy right now to talk specifically about what we've done on the BOW IP and the platform. Any questions before we jump into that area?
Okay, maybe one question on the slide, like going back to where you talked about like things that you could change. So when you talk about this platform, you were saying that on top of this being a chiplet, you kind of imagine various different, let's say, flavors of such an I/O chiplet that would be still designed monolithically to account for these different changes, and so you would ultimately end up with different versions of something like this. Is that right?
Yeah, we wouldn't build it, but that's part of the enablement that we want. As I mentioned, as a foundry, I'm into manufacturing, but Cadence, Fraunhofer, some of the other partners are coming in, is going to have this available. They can do customizations. They can make it available to our end customers as well. So yes, the whole goal is to say, here's a platform that's been proven. We know BOW talks together. We know that you could do a chiplet. It's been proven from a functional standpoint. Now optimize it. What do you need? What memory do you need? You can optimize it for that. The layout. Do you have a power envelope that you want to target? You can do that. We didn't take any of that into consideration, right? But for your particular application, you might need more performance. You might need lower power. That's where you can start customizing it to your particular needs.
Okay, makes sense. Thank you.
A follow-up question to Marek's is, if let's say somebody wanted to replace the bow with UCIe, or replace the memory with replace the PCIe Gen 6 with Gen 5 as an example, right? Do you guys by any chance have a model on how much faster it is to start with this platform versus doing everything on your own?
Honestly, we haven't modeled it. I've modeled it generically with just having a platform versus starting fresh, but not specifically for this chiplet.
Okay. Well, if you're interested, if you or your group is interested, I think we'd be interested in that. I don't want to speak on Marek's behalf, but this would be an interesting topic. There's quite a few people who have had very similar questions.
Okay. Yeah. Let's definitely talk about that. I think that's why we brought throwing it out there. I think these are the things that we want to do. Is any way we can help accelerate this economy and ecosystem, I think is better for all of us.
So we're open to all of this.
But Bapi, your question was to replace the PCIe with a different generation PCIe, right? But that's
Right.
embedded in the SoC.
Correct. So, it's not exactly
trivial.
it isn't, but maybe there's some way you can design this platform as a SoC that makes that somehow, is there a model where using this as a starting point can be shown to be faster, cheaper?
Yeah, Anu, think of it this way. Yes, you're right. It's in the SoC itself and it's work.
Mhm.
But versus
Right.
starting from fresh and building it versus I already have PCI 6 there. Swapping out a PCI 5 and having the hooks in there already, because you've already done it with PCIe, is going to be a lot faster and easier.
Yeah, no, I understand. So Kevin, I totally agree that, and this, everything else is proven, so it makes it much easier.
Yeah.
Okay, understood.
Yeah. But the hard part is this: is if I want to switch from DDR to HBM, now that's a whole different story, right? Because with HBM, you're going to have to switch to silicon interposer. That's going to be
Correct.
different. Okay, so it really depends on what you're trying to change. But to me, having something that's proven as a starting point is always a lot easier and reduces your risk.
It is. It would be great if we could find a way to quantify that somehow. We're really interested in that.
Okay, that'd be a great conversation.
Kevin, do you have a size of the chip in 5, just as a rough guide, so that?
I'm going to leave that for Andy. Can answer that. He was doing the design, so I don't have any of that information right now. Okay. I believe it's smaller than 100 square, but I'll let Andy answer that in a little bit.
I would say it's round about 100 square, exactly 100 square for this chip.
Excellent. Thank you.
Okay, all yours, Andy.
Yeah. Okay. Yeah, then I will take over here for the next part of the presentation. So I want to talk a little bit more about the details of our bunch of wire implementation and also some topics regarding this interoperability. What Kevin mentioned, what we have seen here, which problems popping up if we discuss with partners interoperability and how we can, what is maybe also needed in the future. For our bunch of wire interface, we want to implement different modes. We want to implement the fastest mode, the 16 gigabit mode, but also the slower ones, 8, 4, and 2. We are not implementing yet all the sub modes, the different modes for 8 and 4. We decided for this one, but important for us is that we also have slower modes inside our 5. Because we also see customers, they, especially on the sensor market and automotive market, they are if they want to connect to analog parts, they doesn't need this highest data rates, and then it's important that we also have the slower modes in. Kevin, can you go to the next slide, please? Yeah, and on our TX side, we implemented a first version of the we are also working now on the next generation. So with the 32 gigabit, hopefully we have also a version with 32 gigabit then during this year. All the results we have here, it's for the 16 gigabit version. We have implemented this. We have implemented this the TX. And we have taped it out and measured. We have here the data for the differential clock and also for the single-ended clock. We fulfill all the requirements they are given by the bunch of wire standard regarding jitter and also the A diagram. And we have at this point we have a good for the single-ended one. We have a energy of 0.27 picojoule per bit. We also see here the measured results on the top right side.
Hey, Andy.
Yes.
One quick question. Was this using an advanced packaging? I forgot. I know Kevin showed that. I wasn't sure I understood.
No, the measurement themselves was done only on the wafer prober, so currently without a package. So the characterization was...
No, what I'm trying to say is the interconnects between the both PHYs.
Yeah, we choose here a pitch with round about 130 micrometers.
Okay, standard. Yeah, got it.
Yes,
Thank you.
standard,
Exactly standard.
standard organic. Yeah.
Yeah,
Got it.
right. I'm not exactly sure if it's 130 or 110, but definitively something that we
Sure.
can do with organic materials.
Yeah, thank you.
Hey, Andy, two questions.
Yes, for sure.
One is you're the first, I think you're the first open guys, or at least a research institute to do these measurements. Is there any chance you can sort of publish a paper on how you measured and share that with everybody?
Some paper for the ODSA or
Well, for wherever you
internal.
want. Just something that we can circulate saying, okay, this is how you measure the performance of bow interface, etc. Anything that you can, is that shareable?
Okay, yes, I think I can discuss with my colleagues and that we can share it, what we have done here.
I think that would be really helpful to us and to the bow group, if you can.
Okay, yeah, we will discuss it internally for sure.
Thank you. And the second question is, when you get a chance, can you also elaborate on the demand for the slower? This is something that Marek has brought up. Other people have brought up the sort of the slower bow modes as well in other domains that you were talking. You sort of said, hey, sensors and automotive. I heard you right.
Yes, we see the slow modes especially on, we see it in sensing and automotive. So especially on automotive, we see it because then we have different chiplets that have to run on the high speed mode because between different compute dies, but we also see then some interfaces going to older analog nodes. And it doesn't makes any sense then to use then a different interface. It makes then sense to use then also bow for that interfacing, but then we only need low speed interfaces. Yeah, because the data amount of data to an analog chip is not that high as between two compute dies.
All right, thank you.
Okay, Kevin, can we go to the next slide? So we're also working on the RX side here. You can see here the data after the data recovery, and then also the data on the output side. Also here, we fulfill the requirements following the bow standard. This part is not taped out yet. We want to tape it out in next iteration, and then we also can show measurement results. So if we go to the next slide, then there is, now we come to the discussion here regarding the file, the link layer. It's clear that currently on the link layer side themselves, there's a little bit more discussion. What are the right link layers? We are here in discussion with a partner to how we can implement our link layer. We want to follow here the approach that we have the configuration of the bow file themselves and the link layer by APB interfaces. We also want to include here an I3C bridge to this APB, because this is also what we learned, that it's helpful to have this bridge so that you can configure your chiplets from the outside via this I3C, because you have to do some setups on the beginning. And this is can easily be done by I3C because the number of pins is very low compared to some other interfaces. And currently we discussed this CHI interface to transfer the data on top of this bow interface. Also some other standards like an AXI bridge is also in discussion here internally. Currently we are looking for a CHI interface at this point. But we expect here also more discussion in this bow consortium in the ODSA. What are here the right protocols? And we assume that we need different protocols, link layers on top of this PHY. What we also see here is that we need interfaces for raw data, especially if we also want to transfer analog data, as I mentioned, for example, to connect sensors and so on. Then this CHI and AXI protocol is not the right one. Then a raw data protocol would be very, very helpful, and this is something that should be standardized on top of this bow PHY. we are very interested here to work also on such analog raw data analog standards, because we see here a need definitively from our partners.
So I can comment that the link layer that we're using is the link layer that was submitted to ODSA as to try to standardize on the link layer. So we are implementing that version of it.
Oh, that's right. Like we're, I think it's Madhut or somebody who attends the we would like you guys to actually, Andy, I'll follow up with you offline to attend the link layer program, because we're working on the control path right now, what you have marked as the APB stuff.
Right.
So
yeah, so I want you to be aware of that. Is yes, we're not developing a custom link layer or anything else. We have
fantastic.
utilized what was submitted to ODSA as proposal. I don't know if it's been ratified or what, as a proposal to standardize. So this is that implementation.
It is. It's now a spec.
Yeah. Okay.
Yeah. But yes, that's true. But again, we see also missing protocols here, as I mentioned, for example, a raw data interface, for example, for analog data. This is definitely something that we see,
Oh, yes.
where we see
Streaming,
a
right?
market.
You mean a streaming?
Yeah, streaming to stream, for example, analog data from a sensor as an example.
100%. Actually, this was something we were discussing literally yesterday. So we need to sync up offline.
Okay, yeah, for sure, we can do that. Great. If we go to the next slide, then Kevin mentioned it before. We are working currently to get our test chip running together with a different test chip. What we have here, as Kevin mentioned, we have then two different bow implementation on the file layer. We have the same implementation on the protocol layer. But now a lot of discussions are popping up, and we see also a lot of issues open, or we have a lot of open questions. We have a lot of discussion, for example, we have a lot of discussion on the interoperability on this file level. And we see here that certain things are not really standardized, or that we need more maybe also models. So the question is, or we figured out that it's difficult on the beginning to check the interoperability on the file level. So if two partners has an own file implementation, later on, if both follows exactly the bow implementation, then it should work, as it also is done on PCIe or established standard. But on the beginning, if the standards themselves are not that hardened as older standards are, we see that we need different, we assume that we need models, behavioral models, analog models, and this is currently not really available. So every party can provide such things, but it's also not standardized, also not clear on the community which models every implementation should provide. And this is something where we have a lot of discussion currently to show the interoperability with this other side. And that's an open topic for us. We see then the same discussion how we can make sure interoperability on the link layer. It's also a discussion because the link layer is then also connected to the system on both sides of the chip. How we can make sure that this transmission, that the integration of the link layer into the chiplets can also be checked on both sides. And this is what also Kevin mentioned. It's not only an SoC. We have on both ends, behind this link layer, we have systems, and we have also to bring up both systems, things like that, boot processes. And also for this procedure, it's currently the interoperability can't be really tested because there also at this level some models are missing, how you can make sure that one chiplet can boot the other one, that the right data are transferred, things like that. So this is what we currently see, what it makes very difficult and what needs a lot of discussion bilateral discussion to make sure such interoperability. But if we really want to have a library of or building blocks later on that can easily be integrated together, then we need here more interoperability checks, more maybe also definition standards, things like that. So at this levels, we see different missing standards, missing procedures, methodologies. Questions or comments at this?
Again, I'd say we'll engage offline, but we're hitting roughly these questions in the fire and link layer meetings. So maybe you'll have a more deeper dive on our Wednesday and Thursday meetings on these issues.
Okay, good.
This is very, very helpful. Thank you.
Okay, then I want to explain a little bit more. As Kevin mentioned before, we to get such a chiplet interface, chiplet system running, it's not only to build the chiplet themselves, the chiplet system themselves. You also need a complex environment outside of the chiplet. We are building here also an development board, so we want to we have an ARM-based development platform, because ARM-based platforms are existing. You have a huge variety of different providers of such platforms, and we want to build here an plug-in card for such an ARM platform. And then we can use this ARM platform to enable the hardware software programming. We have also then additional interfaces on the outside of this platform, and we can use this platform, as I mentioned, to start the bring up of this chiplet system. We have to develop then, or we have existing firmware that we can use also for the Tensilica course, but we have also to develop own software. We have developed application stacks and things like that. But the advantage of this ARM platform is that we also can use existing software, so that we have a good software environment here, hardware environment that helps to bring up such complex systems. Okay, next slide. We have this solution here, or what we have here in general. It was a question before. We want to show in general the interoperability, but we also want to show design flows, design methodologies. It starts from the chip themselves, but on the end, we also need the chip package co-design. We have to develop then also the interposer, the organic interposer for that system. So here we use the tools from Samsung, also the hardware from Samsung for emulation, for prototyping, the reference platforms, the reference flows to get the chip themselves running. And we use also the multi-die 3D IC flow for the co-optimization of chip and package, and also the package design. To get the whole silicon as chip working, but also the whole system, the whole chiplet as a chip package board solution running, and get it fulfill all the requirements we have also in signal integrity, power integrity, and things like that. On the end, as Kevin mentioned, it's a platform, such a chiplet solution. We have here some application in mind. For example, we have the Tensilica course in. So with the Tensilica course, we can do a lot of vision application. We have the chance also to do, we have also some course in for AI application. So, or to let run AI software, so we can combine the vision together with AI, and it makes, we have also PCIe interfaces, so we can extend, or we can put cameras on this chiplet, and then the idea is to let run complex application on vision, and it's a chiplet system. And what we also want to show is that we can connect certain of our minimum 2, maybe also 3 of our chiplets together, and then we can also distribute the application to the different chiplets, and then we have much more compute power compared to a single chip solution.
Yeah, so the goal here is by building this is kind of a shift left on the software as well. I know most of us are hardware people, and we're talking about building the chiplet itself. But if we have some of these chiplets on boards, with DSPs built in or FPGAs built in, software people can actually start developing software stacks and applications based on that particular chiplet. And from an economy standpoint is you could say, I have a DSP chiplet that has this software stack already available, and I can integrate it with a separate IO hub with this DSP, and I have an application ready to run with software already. So that's kind of the thought process around that.
This is actually quite exciting. I'm wondering if there's a chance to demonstrate this at OCP Global Summit somehow.
Yeah, I think once we're at that point, we're going to do that. So for example, and this is the concept from Cadence, is Cadence has this, they want to be able, the goal of here is to have boards, and they can go to their ecosystem software partners and say, here's a board to each of these partners, and they can build a real application on top of it. So we can actually demonstrate these chiplets functioning rather than say, oh, I have this chiplet in here's the die. We can actually say, hey, we put these 3 chiplets together on this platform, and look at, here's application 1, application 2, and application 3 running. So I think, Cliff, yeah, we should talk to you guys about that. I'm sure Cadence would love to demonstrate that at some point.
Okay, well, there's going to be a couple things. There's a call for demonstrations that's going to open or is already open for the OCP Future Technologies Symposium, and that might be an avenue. There's also the call for papers that's now open for the Global Summit, and it might be good to put in a proposal for the Experience Center, or that's going to open after, where we can find a way to showcase this. So let's coordinate there. If it's possible to have this ready in time for Summit, we'd like to find a way to work it in.
Okay, sounds good. So actually, I'll just summarize. This is our last slide. Is the goal of all this is really enabling the chiplet ecosystem. We want to help drive the industry in that direction. I think silicon proven platforms is a good start in doing that, enabling innovation, accelerating the design, lowering the risk. I think those are all things that all of us kind of want to achieve, right? If you could build chiplets and allow your teams to innovate, but have a starting platform to accelerate, why reinvent the wheel? You don't need that. Some of the base things are already there. Leverage it as much as possible. That lowers your risk, and that way allows you to focus really in on the innovation that your companies can do. As I mentioned, this isn't going to be done by one company. We need an ecosystem. We need to work together. We need partnerships. That's why Fraunhofer for us is doing the design and the IPs. Cadence was providing some of the IPs, the systems, the methodologies, the flows. Samsung was doing the manufacturing and packaging. And the goal is to expand that. As I mentioned, once we started this, it was just the 3 of us, but we've already expanded to 3 additional partners in this endeavor with memory, with interoperability, with the heterogeneous integration as well. So we're trying to do this. We're trying to expand and enable other partners as well as much as possible. So working with OCP, ODSA, we're excited about things. I know this has come up with a lot of further discussions that I think we can do deeper dives on, and I think that's a great thing. So hopefully this, the short presentation gave you an idea of what we're working on, how we might be able to work with you, how we might be able to work with OCP and ODSA as well. So hopefully this was helpful for all of you guys.
This is fantastic. I appreciate Andy taking the time to stay up. Was it on a 5 p.m. on a Friday evening? Thank you. But any other questions? This is awesome, and I'll send you guys a detailed email offline. But I believe there's a lot of places where we can have a deeper exchange or deeper interaction.
Yep.
Any other questions for Samsung? For Andy or Kevin? I'm front.
Okay. Hey, thank you for letting us present. We appreciate it, Cliff, and we appreciate it, Bobby.
Yep.
Excellent.
Also, thank you from my side to have the chance to present here. Thank you.
Okay. Same here. Thank you for staying up, Andy. And let me do a quick call for opens. Anybody have any opens? If not, Marek, are we on this bridge or a different one?
We're on the other one for the subgroup meeting.
Okay, in that case, then we'll end this meeting. Thank you all. Have a good weekend and everything.
Have a good weekend, everyone.
Andy, thanks again.
Bye.
Thanks. Bye-bye.
Bye.
Bye.